Okay, let's begin our first lecture video. The first lecture video, we're gonna talk about hypothesis testing. Hypothesis testing. And for hypothesis testing, we have a new terminology, which is hypothesis. So what is hypothesis? So hypothesis is a statement regarding the population parameter. So in statistical theory, there are three types of hypotheses. So let's see the first type. The first type is we're interested in testing the population mean mu less or equal the true value mu null, mu 0, and the alternative capital H with subscript A is mu greater than mu 0. And such hypothesis is called right-sided hypothesis. This is the first type of hypothesis. The second type hypothesis is H null, mu greater or equal than mu 0, H alternative, HA, mu less than mu 0, and this is left-sided hypothesis. And the third type of hypothesis is H null being mu equal mu 0, H alternative mu not equal to mu 0, and this is called two-sided hypothesis. So the first terminology in hypothesis testing is hypothesis. And after we get this hypothesis, we need to test it. So to test it, we have to get some data, to get some information to make decision for getting the conclusion of this hypothesis. So after we know the terminology of hypothesis, we should remind ourselves that we should get a random sample from population. So remember, what is random sample? So random sample we usually denote as capital X1 to capital Xn, I, D, follow some distribution. So most useful one is normal. Sometimes we specify the perimeter mu and sigma square, something like this. So this is just example. Remember that for our point estimation, we need to propose some statistic, which is called point estimator, to do estimation. But in our testing problem, after we establish hypothesis in the first step, and after we collect a random sample from population in the second step, our third step is to apply test statistic, or in other words, propose test statistic. For example, sample mean X bar, and in our testing problem, we call the proposed statistic, the function random sample only, as test statistic. So in point estimation theory, the statistic we use is called point estimator. So in testing problem, we call it test statistic. So the last step is the important step. The last step is no new thing. We need to compute some conditional probability. So let's state it formally. The first step, compute the probability of test statistic being more extreme than the realization small x bar, for example, small x bar. So then the realization of the test statistic given the equal sign in H now. So let's see, what do I mean by this? So let's say example. The example, like, so the first step, we established hypothesis testing. So let's consider this right-sided test. H null is this. H alternative is mu greater than mu null, mu 0. And suppose mu 0 is 75. And second step, we get a random sample, and we given that capital X1, capital Xn, IID following normal distribution with mean mu and sigma square. And mu is the unknown. We would like to test mu, do hypothesis testing on mu, and sigma square is given as 100, and sample size is given as small n equals 64. This is our second step, get a random sample from population. The third step remember, let's recall. Third step, propose test statistic. So in this sample, we propose sample mean, capital X bar, and with the realization we are given small x bar equals 75.14. The fourth step. So fourth step, compute. Let's recall the fourth step. First, compute the probability of test statistic being more extreme than the realization given the equal sign in H null. This is H null. So let's calculate accordingly. So the probability of the test statistic, the test statistic here is capital X bar, being more extreme than the realization. So being more extreme. So in our hypothesizing, we think mu greater than mu now is extreme. So being more extreme means cases in each alternative. So here, the fourth step asks us to compute the probability of test statistic being more extreme. More extreme means cases in each alternative. Then the realization. So the keyword here is then the realization. So we have to plug in the realization. So the test statistic being more extreme. So being more extreme corresponds to this greater sign. Extreme than the realization, small x bar, given the equal sign in H null. So the equal sign in H null is mu equal to mu 0. We compute this probability. So this probability is straightforward to compute with the help of standard normal transformation, which means if we transform capital X bar minus mu divided by sigma divided by square root of n greater than small x bar minus mu divided by sigma divided by square root of n, mu 0, because we have given mu equals mu 0. Since we have plugged in mu equals mu 0, then this conditional sign is omitted. And this is what? This is just the probability of standard normal z greater than capital X bar. This is realization is known, mu 0 and sigma divided by square root of n, mu 0, sigma, and small n and capital small x bar are all given. So let's just plug in. So we plug in. We know all the values x bar, mu 0, and small n, sigma square. We need to plug in. And this value equals what? This value equals 0.12. And you can check this table of standard normal. This probability of capital Z greater than 0.12 is what? It is approximately 0.4. So what's the meaning of this probability? Let's recall the fourth step. The fourth step is compute the probability of test statistic being more extreme then the realization, of the test statistic given the equal sign h now. So this probability, let's see this specific example. So this probability means h now. So the equal sign h now is mu equals mu now. The equal sign h now supports such realization. The realization is this small x bar, or realization being even more extreme. So greater sign is being more extreme. So which means if h now, if the equal sign h now is true, then the probability of we getting this realization, small x bar, or even extreme realization, the probability is 0.4, which means if h now is true, we can get such realization 75.14, or even more extreme. More extreme corresponds to h alternative. For example, 80. We can get even larger values if h now is true, if the equal sign h now is true. So while here we write mu equals mu now, not mu less or equal to mu now, and this you can prove mathematically. This conditional probability and the equal sign will give the same result for hypothesis testing. That's why we just given the equal sign h now, not the original. So what do I mean by saying this? So just keep in mind that we write it as original h now, then the conditional probability is the same thing, and that's why we just here write mu equals mu now, not original h now, but we want to show that this thing mathematically they are equivalent. So just keep in mind it is a fact, and keep in mind it is okay to do in this way. So then you can interpret this probability as what? So this probability is given h now is true, given h now is true, the probability of more extreme realization, probability more extreme realization. So in our case, in this specific example, given h now is true, we got probability of more extreme realization being 40%, which is very high probability, which means the decision we should make about this hypothesis testing is to not reject h now. Why? Because if h now is true, we can get such realization or even more extreme realization which supports h alternative with high probability, which is 40%. This is just starting example. We will do more example later. Now you see the 4 steps for performing hypothesis testing. Let's recall. First, establish the hypothesis you are interested in. The second step is drawing random sample from population. And third step is propose. This is this is the choice. This is your choice. Propose some test statistic. So here the terminology is called test statistic. Test statistic. And the fourth step is calculate the probability of more extreme realization given h0 is true. And the trick is here, h0 is true, it can be just plug in the equal sign in h0. So this is fourth step. And if this probability is large, we not reject h0. If small, reject h0. Now you may have one question: how large or how small? How can we decide? How can we make a decision accordingly? For example, how about this probability is 0.1? What should we do? Reject or not reject h0? So then we need to introduce the concepts of error rate. So why we are interested in error rates? Error rates can help us to propose decision rule. So let's firstly see the definition of error rates. So keep in mind, we introduce error rates to propose decision rules. Decision rule means we need to decide reject or not reject h0. So what is error rate? Let's see the definition. So we like to make a right decision, right? So not reject h0 is one choice of decision, and reject h0 is another choice. We just have two choices to make decision. But what is error? Error means when h0 is true, when h0 is true, we reject h0. It is a error, and we call this type 1 error. And h0 is true and we not reject now, we make a good decision. So for h0, for the case of h0 is not true, we not reject h0 is a correct decision. But if h0 is not true but we not reject h0, then it is also an error, and we call this type 2 error. We denoted type 1 error as alpha, and we denoted type 2 error as beta. So this alpha and beta is quite important in hypothesis testing. Which is type 1 error and type 2 error. You should know what type 1 error means and type 2 error means. These two concepts is quite important. And this table can help you to remember those error rates. So let's see how these two error rates help us to propose decision rule. As I have said, the first step, we have calculated the probability of more extreme realization given h0 is true. But we see for large we not reject h0, for small we reject h0, but how large, how small? So what is the specific decision rule? So we introduced Arrowhead. So let's see how Arrowhead help us to propose decision rule. So I just introduced it to you. In practice, what we do. In practice, alpha is what? Alpha is type 1 error, reject H null when H null is true. Beta is type 2 error, null reject H null when H null is not true. So in practice, we set alpha at a certain level. For example, 0.05 to find decision rule. So in our class, to find decision rule, we just use alpha is sufficient. But in more advanced statistical theory, maybe you also need beta to find decision rule. But in our course, for this semester, we just need alpha to find decision rule. So how to find decision rule by alpha? So remember, the fourth step is the probability. So we still use our example, the sample mean example. So x bar greater. So in our fourth step of performing hypothesis testing, we calculate the probability of the proposed test statistic greater than the realization, given the equal sign in H null. But to find the decision rule, we need to get a constant. So we replace the realization small x bar with constant c. We would like to find c because we would like to propose decision rule given the equal sign in the H null. So here, this is the probability, and this is our way to find decision rule. With the help of alpha, we set this probability as alpha. So what does this mean? So this probability means, so recall that this means H null is true. And we're looking for decision rules. The decision rule cannot be, so we cannot use some realization. We would like to find some constant, and we would like that if the observed small x bar is greater than some constant c, then we reject, not reject. So that's the decision rule means. So with the help, so in practice we set alpha at a certain level, for example 0.05 to find decision rule. The decision rule is just made so straightforward by this formula. And this probability can be rewritten as x bar minus mu 0, same trick, divided by sigma square root divided by n, divided by c minus mu 0, divided by sigma divided by square root of n, equals alpha. So the last step is to plug in to find c. We plug in. This is z greater than c minus mu 0 is 75. In the first example, sigma is 100, the square root of it is 10 divided by the square root of 64, and we set alpha as 0.05, and we find table that C minus 75 divided by 10 divided by square root of 64 is what? Is 1.64, and you can find C. So this is left exercise, it's just simple calculation. Okay, so the first part of the average knowledge is that in practice we set alpha at a certain level, for example 0.05, to find decision rule, and we use this formula to calculate the decision rule. So let's put the decision rule more formal. With the help of type 1 error rate alpha, we propose decision rule. For h now mu less than mu 0, h alternative mu greater than mu 0, so our decision rule is what? If small x bar, the realization is greater than C. So let's see what C is. So if we write C in a more abstract way, let's do this firstly. Here we got Z, and here if we do it abstractly, we'll keep it as notation. We got what? We got C minus mu 0 divided by sigma square root of n is what? Is Z alpha. Remember what alpha means? Alpha means this is the PDF, the standard normal, and this area is alpha, and the corresponding point on the horizontal line is called Z alpha. So this means C equals what? C equals mu 0 plus Z alpha sigma divided by square root of n. Now we get C. C is what? C is like this. So we write decision rule. If x bar greater than C equals what? Equals mu 0 plus Z alpha sigma divided by square root of n. Reject h now. So if small x bar, small x bar less or equal than c equals mu 0 plus c alpha sigma divided by square root n, not reject h null. So let's recall that our original four steps for perform hypothesis testing. So the step 1, step 2, and step 3 is the same, but for step 4, our original way of performing hypothesis testing is to calculate the probability of capital X bar greater than small x bar, the realization given this, and we say that if this probability is large, we should not reject h null. If this probability is small, we should reject h null. But the small or large is not so clear. And later we'll talk about this way of performing hypothesis testing, and this is called p-value. But to propose decision rule, so for decision rule approach, we first introduce error rate. So error rate, we first talk about type 1 error, which is denoted as alpha, and for type 2 error, which is denoted as beta. For type 1 error alpha, in our course, we can solely depend on alpha to find decision rule. So only alpha to find decision rule. And the formula is quite similar to this formula in the fourth step, which is like this. So because we are looking for decision rule, so we have to get a constant. So that's this decision rule means. That's what decision rule means. So we just replace small x with capital C, small c, and we, with the help of standard normal transformation, can find in this hypothesis testing, in this example, decision rule for this. We got if small x bar is greater than c, reject h null. If small x bar is less than c, not reject h null. So here so why decision rule works? Because in our original 4 steps hypothesis testing, we plug in the realization small x bar here, and since we would like to propose decision rule here, we would like c, and if for c is greater than x bar, then x bar is not that large. Then not that large, so not that large, we should not reject h null, because if x bar not that large, then this probability is large. So to make what do I mean by saying this thing? Let's write it again. And write it again. So in our original first step, what is probability? The probability is capital X bar greater than small x bar. Given h null is true, we just plug in the equal sign in h null here. This probability. And to propose decision rule, we substitute small x bar with small c, given mu equals mu 0. And our original, this is our original, and this is p-value, and large, not reject, small, reject. And this approach is for decision rule. So for C greater or equal than small x, small x bar, what should we do? Now reject. C less than x bar, reject. So let's compare these two approaches. The first approach is the original one, which is p-value, large not reject, small reject. And this decision rule approach, with the help of alpha, is C greater than x bar, not reject. So why does this make sense? Let's compare these two for the not reject cases. So for p-value large, not reject, so p-value large. So if we increase the small x bar, then so if C is greater than x bar, here is x bar. We not reject, which means x bar is quite small, the resistance is quite small. And then if small x bar is quite small, then this probably should be large, and then not reject. So this means these two approaches are quite, although they are different, but they are quite, the decision rule approach and p-value approach are quite make sense in similar way, but they are a little different. But we will go to detail of decision rule and p-value with more examples and more examples to illustrate those things in detail. Okay, so now let's do a quick review of what we have covered today. Okay, first today we go into the hypothesis testing part. So for hypothesis testing, we have 4 steps. The first step is to propose hypothesis. We have 3 types of hypothesis. First is right-sided, second is left-sided, and third one is two-sided. The second step is we should get random sample. This is routine, it's just ID random sample. The third step is propose test statistic. So in estimation theory, we use the terminology as point estimator. In hypothesis testing theory, we use the terminology as test statistic. We begin with the kept x bar example. And the fourth step is to compute the probability of test statistic being more extreme than the realization of the test statistic given the equal sign in H null. So extreme means cases in each alternative, HA. So it is easy to get the first example. So first example is just this right-sided test. The right-sided hypothesis testing, this and this random sample, and we use this sample mean as test statistic, and we compute the probability of more extreme realization given H null is true. We calculate, and this is called p-value. We will go to detail later. We calculate this probability with the help of transformation of standard normal, and we think it makes sense that if it is large, we should not reject H null. If it is small, we should reject H null. But this approach works. You can just set some critical value. For example, if you say 0.1, you think 0.1 is small, then 0.4 is greater than 0.1, then we say A large, so we now reject null. But in statistical testing, another way to do it is to decision rule way. So to go to decision rule, we have to introduce error rates. So error rates, just with the help of the table, you can memorize 2 error rates, type 1 error and type 2 error. In practice, in our course, we just set alpha at a certain level, for example 0.05, we can just find decision rule. So what's the usage of beta? We will talk about later. So how to utilize alpha to find decision rule? We use this formula, and we can also use with the help of standard normal transformation. We can find C So then for the same hypothesis testing problem, the decision rule is as follows. And then to close this section, we compare the p-value approach and decision rule approach. So this original p-value, large null reject, small reject, and the decision rule approach here, C, you should find C, what C is. So C greater than X, small x bar null reject. C is less than small x bar reject. So there are two different approaches in hypothesis testing. So for the introduction to hypothesis testing, we should remember two approaches. One is p-value approach, one is decision rule approach. And we just covered this first example, this hypothesis testing, which is right-sided testing like this, and normal model. We have got what we are interested in. So with the help of alpha, type 1 error rate, we can propose decision rule approach. So what is the use for beta, the type 2 error? Let's talk about beta now. So beta, type 2 error. So for beta type 2 error, it is. So we interested in 1 minus beta. So beta here, let's see the table. So beta is the probability of null rejection now when each is not true. So here, so 1 minus beta is the probability of rejection now when each is not true. So this is correct. So in practice, we are interested in this part, 1 minus beta. Why we're interested in 1 minus beta? So alpha is help to help to find the decision rule. So beta actually is a criteria to assess the decision rule. Let's make it. Let's write it. Criteria to assess decision rule found with the help of alpha. So let's put it formally. So what is 1 minus beta? 1 minus beta it has a specific name in statistical theory. It is called power. Why is this terminology? Let's see what do I mean by saying beta as 1 minus beta as power. It is a measure to quantify the ability of the proposed decision rule to capture the deviation, capture the deviation from H now. So this sentence is not that useful. So the next sentence is quite useful. So in practice, we assign a specific value to mu. Now the true value, the specific value mu star to mu now. So what is the definition? 1 minus beta. So beta, remember, it is type 2 error rate. So what is type 2 error rate? Type 2 error rate is to the probability of, so 1 minus beta is 1 minus type 2 error rate, which means we make the correct decision. We make the correct decision here. We make the correct decision. We reject H now. So reject H now is capital X bar greater than C. But for decision rule, we actually, the decision rule is C equal greater than small x bar. But to quantify uncertainty, we have to. So our decision rule originally is small x bar greater than C. But here we would like to quantify the uncertainty. We keep capital X bar greater than C. Then we, in this case, reject given mu. Here we reject now when H now is not true. 1 minus beta rejecting H now is not true. So let's go over the definition of 1 minus beta. Beta is measured to quantify the ability of the proposed decision rule to capture the deviation from H now, capture the deviation. So I think maybe decision rule here, we do not write small x bar, we write capital X bar, will be better. So 1 minus beta power is a measure to quantify the ability of the proposed decision rule to capture the deviation from the H now. So here the keyword is the deviation from H now. So what is deviation? So deviation is case by case. So in practice, we assign specific value mu star to mu 0, which means mu is not mu 0. Here is not mu 0. Mu here is mu equals mu star. Then this is the power. So this is the formula of power. and we would like to calculate this 1 minus beta. What is this? So we still use the standard normal transformation. So here, C, remember we just plug in C. What is C? So x bar C is what? C we have derived previously. So C is mu 0 plus the alpha sigma divided by square root of n. We plug in. But this time, mu equals mu star, not mu 0. So for this probability, so what is this? So remember the derivation for this, for the C. Here, sorry, I forgot this. Okay. And since we would like to use the information that mu is actually mu star, not mu 0, we minus mu star plus mu star, minus plus trig. Since we have used the information here, we don't write it, we omit it. So this we can write the left hand side of the inequality as two parts. Then since the true mu is mu star, then this thing becomes a standard normal random variable. This is z. So this probability can be written as z plus mu star minus mu 0 divided by sigma divided by square root of n greater than z alpha. Finally, we got the power function, which is z greater z alpha plus mu 0 minus mu star divided by square root divided by square root of n. So this function is denoted as 1 minus beta. This is the power for this hypothesis testing. Okay, so I think this video will have a lot of new knowledge in this video. Let's make a short review. So for hypothesis testing, we have 4 steps. First, establish a hypothesis. Second step, get random sample. Third step, propose test statistic. In this first lecture video, we just focus on this sample mean. The fourth step is compute the probability of test statistic being more extreme than the realization of the test statistic given the equal sign in H null. So extreme means case in H A. So this sentence is quite important because it's the definition of p-value. And we constrain ourselves to this right-sided test. and the normal model, sigma square is known. So for a p-value approach, if the p-value calculated is large, not reject now, small reject. So we also introduced the decision rule approach. Decision rule approach is established with the help of error rate. So in practice, just type 1 error alpha is sufficient to find decision rule. We use this formula, the probability of capital X bar greater than C given mu equals mu 0, which is H naught is true, equals alpha. We can find constant C. Then the decision rule for this hypothesis testing is if small x bar greater than C is reject null, small x bar less than C, not reject. And we compare these two approaches. One is p-value approach, one is decision rule approach. And here, so keep in mind, no matter small x or capital X bar, when you do it practically, you just use small. When you want to quantify the uncertainty, you just use the capital one. So that's the principle. So just alpha can help us to find decision rule for decision rule approach. Well, so what's the usefulness of beta? So for beta is the criteria to assess decision rule found with the help of alpha. So 1 minus beta, we have a terminology which is power. So power, it is a measure to quantify the ability of the proposed decision rule to capture the deviation from H null. So to capture the deviation from H null, in practice, we assign a specific value mu star to mu null. So this is the formula to calculate power in this case. And we show how to do this one more step by step. Okay, so this lecture finished. This lecture is just elements of statistical hypothesis testing. Okay, see you in next lecture video.